Okay, in this video, we will discuss about the physical properties and the molecular structures. More particularly, a question and answers of physical properties and molecular structure chapter, which comes under inorganic and physical chemistry. The code is DSC 7. Let's look into the syllabus. Uh, syllabus contains a dipole moment, polarization, and the orientation of dipoles in an electric field, Clausius Mossotti equation, electrical properties of the solids, types of solids, metals, insulators, and the semiconductor, pyroelectricity, piezoelectricity, ferroelectricity, inverse piezoelectricity, definition, and examples. Thomson effect, See-beck effect, and Peltier effect, definition with an example. Let's go to the first question, that is define polarization. The phenomenon of distortion of electrostatic field of a molecule causing the changes in equilibrium position of a nuclei, separating the centers of the positive and negative charges is called polarization of the molecule. Then the positively charged nuclei is attracted towards the negative electrode and vice versa. Let's go to the one more question, that is what are polar and non-polar molecules? Give two examples for each. The polar exists in heteronuclear molecules. Heteronuclear molecules means HCl or HCl. HCl is called hydrochloric acid. HCl is called hydrogen cyanide, where the shared electron pairs are displaced towards the electronegative atom. In these two, chlorine is electronegative atom, Cl will be the electronegative atom. That means the bond between the hydrogen and chlorine, the hydrogen and cyanide, the bond pair move towards the chlorine and move towards the cyanide. That's what the shared pair are displaced towards the electronegative atom. As a result of slight positive charge, that means it acquires a positive charge on the hydrogen, negative charge on the electronegative atom is acquired, and the molecule is known as the polar or dipolar molecule. Then nonpolar exists in homonuclear moieties, homodinuclear moieties. For example, hydrogen, fluorine, iodine, bromine, oxygen. Okay, these are the dinuclear molecules, where the shared electron pairs lies exactly at the center of the two atoms are called nonpolar molecules. So define dipole moment. The dipole moment of a polar molecule is defined as the product of the charge, that means Q, the product of the charge on each end of the molecule and the average distance between the centers of the nuclei. Average distance between the centers of the nuclei is D. Then let's go to the one more question, that is the dipole moment of hydrogen fluoride, hydrogen bromide, and hydrogen iodide are 2, 1.3, 0.8, and 0.4 dp. Arrange them in the increasing order of polar character. Hydrogen fluoride is greater than hydrogen fluoride, it's greater than hydrogen bromide, it's greater than hydrogen iodide. It is the increasing order of polar character. Let's take one more question. Here we are comparing the para-dichlorobenzene. That means para-dichlorobenzene has a zero dipole moment, where para-dihydroxybenzene has a net dipole moment of 1.64 D. Give reason. In para-dichlorobenzene, the two fluorine atoms are present in para or opposite position. The net dipole moment is zero. Why? Because the dipole moments of the fluorines are in opposite direction and they get cancelled as the bond movements gets cancelled each other. Whereas the dipole moment of 1,4 dihydroxybenzene, this is because of the resonance. It's not a zero dipole moment. That means it has a dipole moment. That's because of the resonance forms of the 1,4 dihydroxybenzene. Then Let's take one more example, that is a chloroform has a permanent dipole moment, while carbon tetrachloride does not. So chloroform means CHCl3. So CHCl3 is called chloroform, and you know that three chlorines are attached to the carbon, one hydrogen is there. So, and the dipole moment of the chlorine are in one direction, so it has a permanent dipole moment. So, in the case of carbon tetrachloride, four chlorines are attached to the carbon and they are in opposite direction. That's the reason dipole moments are cancelled each other. Hence, net dipole moment of carbon tetrachloride is zero. Let's take the one more question, that is, explain why carbon dioxide has a zero dipole moment and sulfur dioxide has a positive dipole moment. So carbon dioxide is a linear molecule. Linear molecule means oxygen, carbon, oxygen, double bond, carbon, double bond, oxygen. It's a linear molecule. That means dipole moment is towards the oxygen. That means dipole moments are in opposite direction. That's the reason the dipole moment gets cancelled in the case of carbon dioxide, and it has a zero dipole moment. Sulfur dioxide, because of the presence of lone pair of the sulfur dioxide occupies the bent shape. Because of this bent shape, the dipole moment are in one direction, and it is also having a C2V symmetry of axis, and it has a permanent dipole moment. Therefore, it is a polar point. Let's take one more example, more particularly uh, trans dichloroethane. So in this trans dichloroethane, the dipole moment is towards the chlorine and dipole moment is towards the chlorine. That's the reason dipole moments are gets cancelled. So trans structure, we need trans structure one is the zero dipole moment, whereas the cis one, it has a permanent dipole. So then malic acid possesses a permanent dipole moment, but not the fumaric acid. So you know that fumaric acid means COOH, CH, double bond, CH, COOH. So here in the fumaric acid, the COOH are in opposite direction. Since the COOH groups are in opposite direction, their dipole moments are cancelled. That's the reason fumaric acid having zero dipole moment. When it comes to the malic acid is the cis param one, fumaric acid is the trans param one. Malic acid is the cis param means both the carboxylic groups are at the same side, then the dipole moments are in one direction. That's the reason malic acid showing a dipole moment. Then if we are looking at the applications of the dipole moment, the dipole moment used to predict the shapes of the molecule. Dipole moment, using dipole moment can differentiate between the cis and trans isomer like fumaric acid and malic acid. Similarly, uh, using dipole moment, it is possible to differentiate ortho position, para position, and meta isomers. Then using the dipole moment, it is possible to supports the possibility of resonating structure. So let's go to the another question. So here I'm taking what is meant by induced dipole moment. That means the phenomenon involved in the introduction of dipole moment. Phenomenon involved in the introduction of dipole moment for a non-polar molecule due to the application of electric field is called induced dipole moment. What it means, we are inducing dipole moment to the non-polar molecule in presence of electric field. This is called induced dipole moment. The molecule gets polarized only under applied electric field. Then um, uh, write the Clausius Mossotti equation and indicate the terms involved in Pm is equal to epsilon r minus 1 upon epsilon r epsilon r plus 2 into Vm, that is equal to 4 pi upon 3 Na alpha d. So here, epsilon r is the dielectric constant or relative permittivity medium, and Vm will be the molar volume, Na will be the Avogadro's number, alpha d will be the distortion polarizability, Pm will be the molar polarization, epsilon naught will be the permittivity of the free space. Let's take one more question. So here, a magnetic permeability. So magnetic permeability is the fundamental property that describes the material's ability to allow the passage of the magnetic field lines. It quantifies how easily a material can be magnetized in the presence of an external magnetic field. Magnetic permeability measures a material resistance against the formation of the magnetic field. It is defined as the relative increase or decrease in the resultant magnetic field inside any material compared to the magnetizing field in which the given material is located. In other words, it represents how well a material responds to an applied magnetic field. The magnetic permeability, it is denoted by mu, is typically represented by the Greek letter mu. It is defined as the ratio of magnetic induction, that's called V, to the magnetizing field strength, that is H, within a material. That means mathematically mu is equal to V upon H. The SI unit of magnetic permeability is Henry per meter. That's called H upon M. This is the magnetic field. So more particularly, externally applied magnetic field. Right. I will take one more question. Explain the term magnetic susceptibility. So magnetic susceptibility is the property that indicates whether a material is attracted into or repelled out of the magnetic field. Magnetic susceptibility measures how easily a material can be magnetized by an external magnetic field. It quantifies the degree of magnetization of a material when subject to a applied magnetic field. Materials can exist different types of magnetic susceptibility based on their atomic properties and the composition. I will take one more question. So here, what is paramagnetism? What are the factors contributing to paramagnetism in a substance? The phenomenon exhibited by certain substances which are weakly attracted towards the magnetic lines of force, which lies their magnetism in the absence of magnetic field, is called paramagnetism. The phenomenon exhibited by certain substances which are weakly attracted towards the magnetic field, magnetic lines of force, which lies their magnetism in the absence of magnetic field, is called paramagnetism. The paramagnetism is affected by the following factors: number of unpaired electrons, temperature, magnetic susceptibility, and the magnetic permeability. So I will go to the next slide. What are the paramagnetic and diamagnetic substances? Give two examples each. The substance, when placed in a magnetic field, the lines of force deflect. The lines of force deflect towards the substance. They are weakly attracted by the magnetic lines of force. Its magnetic susceptibility is positive and its magnetic permittivity is greater than 1, are called paramagnetic substances. For example, aluminum, platinum, magnesium, molybdenum, and lithium. The substances, when placed in a magnetic field, the lines of force deflect away from the substances. Its magnetic susceptibility is negative and its magnetic permeability is less than 1, are called diamagnetic substances. Example, copper, antimony, bismuth, gold, and graphite. So I will take one more question. That is, what are ferromagnetic substances? Mention their characteristics. Substances which are attracted by the magnets and can be magnetized are called ferromagnetic substances. Iron, cobalt, nickel. That means substances which are attracted by the magnets and can be magnetized are called ferromagnetic substances. Example is iron, cobalt, nickel. If we are looking at the characteristics, show all the properties of the paramagnetic substances uh, to, to a much as greater degree. The susceptibility decreases as the temperature increases. Magnetic susceptibility is very high. So with this, I will differentiate the paramagnetic substances and the diamagnetic substances. So these paramagnetic substances are attracted by magnets when placed in a magnetic field. Diamagnetic substances are repelled by the magnets when placed in a magnetic field. Paramagnetic, they move from weaker to a stronger parts of the field. Diamagnetic, they move from stronger to a weaker parts of the field. The lines of force tend to close towards the material. Diamagnetic, the lines of force move away from the material. Susceptibility of this material is positive and it is inversely proportional to the temperature. Diamagnetic susceptibility of this material as a small value do not depend on the temperature. So let's take one more question. So here, what are semiconductors? Give examples. Semiconductors are the materials that have a electrical conductivity between that of the conductor like copper and an insulator like glass. This unique property allows them to control the flow of electrical current in electronic devices. They are typically made of silicon, but can also be composed of the other material. For example, group 14 elements are semiconductor, silicon, germanium, diamond. Group 14 compound semiconductors are called silicon carbide. So let's take one more question. What is Peltier effect? This is discovered in 1834 by the French physicist Jean-Charles Athansay Peltier. A Peltier effect is the thermoelectric phenomena where heating or cooling occurs at the junction of the two different conductors when an electric current is maintained through them. This effect is particularly stronger in circuits containing dissimilar semiconductors. This effect is used in various applications, including the temperature control system and the electronic cooling devices, as it allows for heat transfer without moving parts or fluid. Let's take one more question. Explain See-beck effect with an example. So practical example of the See-beck effect using a thermocouple, which is a device that measures the temperature differences. Imagine you have two wires made up of different metals, say copper and iron. Uh, you join one end of each wire together, forming one junction, and keep the other end separate. Now you heat the joined end by placing it near a flame, while the separate ends are kept at a cooler temperature, such as dipped in ice water. This creates a temperature difference between the hot junction and the cold ends. Due to the See-beck effect, this temperature difference generates a voltage across the two wires because the heat causes electrons in the metal to move from hot end to the cold end. The amount of voltage generated is proportional to the temperature difference and can be measured with a voltmeter connected to the two separate ends. Commonly used thermocouple metal combinations include Constantinian alloy of copper and nickel, copper and Constantinian iron, Constantinian chromal, nickel chromium 90 is to 10 composition, and Constantinian aluminal, that is 95% nickel and 2% aluminum. Then I will take one more question. So that is explain Thomson effect with an example. The Thomson effect, named after the British physicist William Thomson, it is a thermoelectric phenomena where that is either absorbed or emitted when an electric current passes through a conductor that has a temperature gradient. This effect is a part of the broader thermoelectric effect, which also include the See-beck and Peltier effect. Imagine you have a metal rod with one end heated and other kept cool, creating a temperature gradient along the rod. If the electric current is passed through this rod, the Thomson effect predicts that heat will be absorbed or emitted depending on the direction of the current relative to the temperature gradient. For instance, if the current flows from the hot end to cold end, and if the metal Thomson effect is positive, and the rod will absorb heat from the surrounding environment at the hot end and releases heat at the cold end. Conversely, if the current flows from the cold end to hot end, then rod will absorb heat at the cold end and releases it at the hot end. The Thomson coefficient, which is a material-specific property, determines whether the heat is absorbed or emitted. It can be positive or negative, and its value changes with temperature. I will take one more question. More particularly, I will take the difference between the piezoelectric and inverse piezoelectric. So piezoelectric means a certain materials can generate an electric charge in response to the mechanical stress. Inverse piezoelectric means an applied electric field causes a piezoelectric material to change shape or deform. So if we are looking at the examples of the piezoelectric, quartz watches. In quartz watches, a quartz crystal is used because of its piezoelectric properties. When a voltage is applied to the crystal, it oscillates at a precise frequency. These oscillations then used to keep time with remarkable accuracy. If we are looking at the inverse piezoelectric effect, ultrasonic transducers are the devices, and these devices are commonly used in medical ultrasound equipment. They operate based on the inverse piezoelectric effect. The piezoelectric material ability to convert an electric field into mechanical energy is a direct application of the inverse piezoelectric effect. This principle is also utilized in speakers and buzzers, where the electric signal is converted into sound waves. Let's continue the difference between the piezoelectric and inverse piezoelectric. Some piezoelectric crystals, when heated, produce electricity to some extent is called pyroelectricity. Example, gallium nitride, semiconductor, and application in LED, pyroelectricity and ferroelectricity. Ferroelectricity means in some piezoelectric crystals, the dipoles are permanently aligned in a particular direction, even after removal of the electric field. Applying electric field can change the distortion of the polarization. These are called piezoelectric solids. For example, barium, titanium oxide, lead titanium oxide, lead zirconate, titanate. Applications, high quality infrared cameras, fire sensors, and vibration sensors. Let's take one more question. What is the effect of temperature on the paramagnetic property of the substance? Paramagnetic property of the substance is inversely proportional to the temperature. That is, that material become more magnetic at lower temperature. Let's take explain the significance of Curie temperature. Below the Curie temperature, the atoms are aligned and paired, causing a spontaneous magnetism. The material is ferromagnetic. Above the Curie temperature, the material is paramagnetic as the atoms lose their ordered magnetic moments when the material undergoes phase transitions.